This is a production of Cornell University.
So what I'd like to do is finish off this component of nutrient management and fertilizers, and this dynamic, environmental dynamics and quality. I think this actually might be a good title for what's going to happen for the rest of the semester. We're going to be talking about this from a lot of different perspectives. From pollution perspective, from a remediation perspective, from a management perspective, from a measurement perspective. So I think when I say don't follow on the calendar as to the lectures for the next, I guess, for 7 lectures left, something like that. Don't follow it, but this is basically what the content's going to be. All right, questions? We good to go? All right, so we're going to be talking about nutrient management. And when we talk about nutrient management, these are the things that you have to keep in mind when you're thinking about how nutrient cycling is working, how you're going to be managing issues of nutrient loss, nutrient gain. You're going to have to be thinking about the mineralogy, the parent material. Okay? You're also, in relationship to that parent material, you're going to have to be thinking about texture. Now, texture obviously has this issue with surface area. When we start talking about texture and parent material together, we're starting to talk about CEC and AEC, so exchange complexes. Okay? We also have to think about the climate. The climate is going to control it, specifically for nutrient processes that are controlled by biological systems. Certainly is going to control water, the amount of water, and the temperature is going to control the distribution and activity of organisms. But water and climate also have to do with, or temperature, water and temperature also have to do with the the chemical reactions with or without biological mediation. Okay? Biology, obviously related to climate, but the type of organic matter and the biota and what's going on there is certainly also going to affect how these nutrients are moving through the system. pH, solubility of nutrients. The solubility of these elements is really dependent upon the pH. And then in turn, this pH has a huge effect on exchange complexes. So the retention of those nutrients and how those nutrients move through the system. And then finally, the nutrients themselves. Okay? So today, we're going to talk about availability, nutrient availability. Okay, what is it? It is a vague term. Okay, what is it though? Okay, well, when we talk about nutrient availability, we sort of talk about 3 things, but most people think, well, how much of it is going to get to the plant? Okay, well, how much of it's going to get to a plant has a lot to do on what is the concentration of that nutrient in the solution. Right, and it makes sense. Okay, then once that nutrient's gone, what's the speed of replenishment of that nutrient back into that nutrient solution? And then finally, when it's in the solution, how fast is it going to be moving through that system? Okay, last lecture we talked about the issue of mass flow versus concentration gradients. Okay, that has a huge impact on this mobility. And the mobility of the solubility of those nutrients or those ions in turn have a huge effect on the mobility. They're playing back to each other. Okay? The definition is the ability of a soil to maintain high concentrations. It's not really the ability to maintain high concentrations, but a fertile soil in essence is its ability to maintain high concentrations in solution and in the vicinity of the root. If the nutrients are in high concentration and they're not near the roots, they're not going to do a lot of good for the plant, right? Okay. Now, another definition we should talk about is this definition of what fertilizer is. Generally, people, when you say fertilizer, most people think of it's an inorganic material that you buy at Agway or something like that. Okay? A fertilizer is a material, natural or synthetic, inorganic or organic, that provides useful, notice that it's underlined, useful quantities of plant nutrient in a form that can become soluble in the soil. And in fact, it can be soluble already or can become soluble. Okay? It's dependent upon, or its availability is basically dependent on three factors. And those factors are the ones that we talked about already, these factors. Okay? And the fertilizer, in essence, also builds up the reserves to provide useful quantities. Okay? The definition is really this component of it. Now, that availability can vary from time to time and from soil to soil and from condition to condition. Okay? Availability may vary from soil to soil even when that same amount of nutrient is present in each one of those soils. Now, why? Well, it depends on those three factors again. The concentration of those nutrients in the solution, the speed of the nutrient replacement, and finally, the mobility of that nutrient in the soil. Sorry I skipped back. I know you guys hate it when I do that. Okay, keep those three things in mind. Some of the nutrients can be replenished by organic decomposition. If I have organic matter in my soil, that's going to replenish the availability of those nutrients. Okay? It's going to depend on the kind of organic matter. It's going to depend on the soil water content and temperature, climate again. Nutrients, some nutrients can be retained more tightly in the soil because of higher capacities of that soil to hold on to certain things. The classic example here is the phosphorus one. What happens when the pH of a system goes low? How does the phosphorus bind in those systems? Aluminum and iron. Okay? As the systems become at a higher pH, phosphoruses are bound to calcium. Maximum availability of phosphorus tends to be around 6.5 because you're minimizing calcium and aluminum and iron. Okay? So that's a property of retention. That's a property of the soil that has that's a retention property of the soil that holds on to that. In this case, phosphorus. Does that make sense to everybody? Yeah? Ish, kind of? So, how do we in fact figure out what availability is? And there's basically two methods. One is a soil test, okay, and there are three factors that control this availability, and then a plant response. So let's start with the soil tests. What are the factors that are going to control that soil test? Now, if I'm doing a soil test, and I take a soil and I measure the nutrient availability, and there's a lot of different types of tests that we use. Okay? Most of the tests that we use basically are mimicking the ability of a plant to extract nutrients. It's not a test, and we talked about this in lab. Okay? It's not a test that's going to take a soil and basically completely digest it and tell me exactly what everything is in the soil. What it's going to do is it's going to be a test that can extract or mimic the ability of a plant to extract. This is not a total disillusionment of the soil. Okay? This is basically a wash of the soil. It's washing at a concentration that basically the plants would be able to wash it off. Does that make sense? Okay, so we need to have an understanding of what the concentration of the nutrients are in the solution, not in the total volume. Okay? We need to have an understanding, if this test, if it's going to be effective, needs to have an understanding about the speed of the replacement of that concentration in the soil. Okay? Now, it may, in fact, not be the test, but it may be interpretations based on the test. Now, when we did the submissions for Dillman Hill, part of that submission test was we want to know what these nutrients are, and this is the type of plant that we have. But we also gave a lot of information about the soil type and its location. Well, why did we do that? A lot of that had to do with this. I wanted to know what type of soil it is so that I have some sort of idea about so I have some sort of idea about CEC and the ability of that system to exchange these nutrients on exchange complexes. Right? If I just give you a measurement of this, I'm not going to have any idea about the measurement of replacement. And then finally, depending upon what kind of nutrient it is and in what kind of soil it is, I have an understanding of the mobility of that nutrient in that particular soil. Does that make sense to everybody? Questions? Should I restate that? Yes? Okay. So let's think about this. If I need to have a test that tells me about nutrient availability for my plants, or for whatever, I need to have a test that will mimic the plant's ability to extract that material. Does that make sense? Okay, and that's why I want to have sort of the concentration of the nutrients that are in the soil solution, but I also want to have an understanding about the speed of replacement. Okay, because if the plants can only extract a little bit, there's not going to be a lot of replacement. On the other hand, if the plants can extract a lot, there's going to be a lot of replacement because of the cation exchange capacity. Does that make sense? Also, potentially weathering reactions. Does that make sense? Now, for me to be able to give you that type of information, I can't strictly depend upon a test alone. I need to have some sort of understanding about what kind of plants you're growing, because I need to know what their lifestyle is, but also their ability to extract stuff. But I also need to know stuff about the soil that they're growing in. Okay, if I just have the liquid of the soil that they're growing in, it doesn't tell me anything about the surface areas of the soil that they're growing in, the solid part, right? That's why we ask questions about the soil. Does that make sense? Cool? All right. The second way we can basically figure out what's going on, or a sort of an assessment of nutrient availability, is basically the plant response. Okay, I can put a plant in the soil, okay, I can give it a various amount of nutrients, and I can look at its response to that soil and the amount of nutrients that I add. These are field trials. We do this all the time. And this is basically the basis for many of our interpretations of these soil tests. What we do is we go out in the field, we plant these things, we give it a variety of different nutrients in a variety of different soils. We see what this response is, so that when we get your soils or for anybody's soils, we have a number of where that nutrient is in the system, i.e. how much has been added to the system, and we have a measurement of what kind of soil it is, and we know what kind of plant is growing. So we just basically correlate that soil test with the response curve, and we can give you an idea about how much you have to add to get to this point. Does that make sense? Yes? Is it? I'm definitely going to start a coffee business in here. All right. And again, it's based on these three characteristics of availability. Sure.
So number 2 is speed of nutrient replenishment. And I know you say it's vague, but I mean, understanding the context in which the soils are in, how would you express that in terms of, would that be reflective of quantity of nutrients, or?
All right, so the question, let me restate the question. The question is, in reference to, how would we communicate this issue of speed for replenishment? What does that actually mean? How fast something is? Is that in essence what you're asking? Yeah. So if the plant starts sucking nutrients out of the soil solution, how fast is that response? It's a good thing I can return the answer, because I feel like I'm a really good Cornell student. I can spit back the question for you, but I don't necessarily know the answer on that one, because it's going to be really dependent upon the different types of nutrients. Some of them are going to be very quick, potassium, bang, okay? But on the other hand, potassium can also bind fairly well with things. Calcium is going to be something that's really, not calcium, phosphorus is going to be something that's really slow. And I think the speed has less to do with the actual time and more to do with the plant. So if you think about replenishment, certain plants, all plants, they have certain stages of their life that they need to have certain nutrients. Now, in general, we all have sort of base requirements, but when they go into fluorescence or they seed set or something like that, during those periods of time, they have some sort of like peak need for certain nutrients. And that's really more about what we're trying to, it's not like base numbers that we're trying to give them. We're trying to give them the amount of nutrients they need at their stage of life.
So it'd be a timing.
So it's more a timing thing. So,
Earlier.
right, so classic inorganic fertilizer amendments, it's you don't put all the fertilizer at the beginning of the season. You go in there at certain times of the year and you side dress, okay? And you give the fertilizer when the plant needs it. And this is a really good example of when you really want to do this is sort of middle of the road type of fertilizer, but you really want to have some base level fertilizer in the soil. And this is classic organic sources. You know, if I put organic material in there, because organic matter decomposes slowly, I'm going to always have this baseline of nutrient availability. And then I got a certain crop in there that goes, at one point, it really needs a high demand. Well, my organic fertilizer is not going to hack it because it's just not releasing the amount of nutrients that plant needs at that particular time. And the argument there is that, well, then we go in there with some sort of quick release fertilizer. Now, that's an argument that, that there's a lot of room to argue about whether that's the way or not. But the reality is plants need to have some sort of base level, but then they also have to have these peak points in their lifestyle, in their nutrient demands, okay? And that's where you sort of think about what this is. There is not any hard and fast rule that says nitrogen is going to be off at this, potassium is going to be at this, calcium is going to be at this. It really has to do with the type of soils that you have in the system and what's actually in the concentration of the soil solution, because it's an exchange between these two. Okay? Does that make sense to everybody?
This has been a production of Cornell University, on the web at cornell.edu.